So tomorrow's test will be in 414. I'm pretty sure that's where the beds are, the mannequins and stuff. Okay, that's where we're going to be, where we've been. Remember the deal about the write-ups. They're due. They're always due the next week. And if you have basically the calculations, which involves graphs and a copy of your lab notebook to give to me when you come take your test at 1, that's all you have to do. If you don't, then you have to add the stuff ahead of it. Okay. Friday, I'll return your graded exam. We'll go over it, and then we'll keep lecturing on Unit 3. I'm hoping that tomorrow, Friday lecture, we'll have enough time, so I might not spend much time going over the exam because I want to finish that first part. And next week is spring break. Yay! So you already know there's going to be a K. I've already complained about the K, right? But we really do need to kind of go on. It's a capital K. So the title of this is we're going to be switching gears from looking at rate law expressions to looking specifically at reactions that are in equilibrium. So you're going to have to see a two-way reaction arrow. Okay, systems that are in equilibrium. So we could generically write it this: will reactants proceed to form products? And we'll be talking a lot about this, that actually products go back, proceed to form reactants again. It's a back and forth sort of thing. And the whole equal and equilibrium means that the rate of reactants going to form products is equal to the rate at which products are going back to form reactants. Okay. So this is kind of cool. If you kind of think of it, it's important that if it's at equilibrium, then the concentrations are steady. The concentrations of reactants and products, there's no change in them. Although it's dynamic, okay, there's no change in the molar concentration of the reactants and products. So here we have 3 different scenarios. It's all the same chemical equilibrium where CO reacts with H2 to form CH3OH, right? Chemical equilibrium, back and forth. So it says 3 approaches, and all it means, the approaches, means different initial concentrations of everything. So here's your key up here, where we have 2 reactants and 1 product. Okay. So here, basically, they're saying we have 1 molar of both the reactants. Okay. And notice that the product is 0. Actually, the initial concentration of the product is 0. Okay. Given time, when the dust finally settles, can you see in this gray area that that's your steady state? What does it mean by steady state? It means the molar concentration of your 2 reactants have dipped to a concentration they're going to stay the same. The molar concentration of product is staying the same. Okay, if we compare that to this one, check this out. The product is 1 molar, okay, and the initial concentration of each of the reactants is 0. Hey, you can do that. Kind of interesting. It's a back and forth sort of deal. Okay. Again, the gray area, what's significant there is that it's leveled off. The molar concentration of all 3 things, the 2 reactants and the product. And then last but not least, we have a scenario where we have 1 molar in everything. It's kind of fun. It's like the floodgate. You have to me, you have to have a partition. You have to have your 2 reactants, 1 molar, your product, 1 molar. You lift the partition and you let it go. Okay? And when the dust finally settles, these are your equilibrium concentrations. So where it says gray, so where it is gray, those hash marks are your equilibrium concentrations. Lidrium. Okay. Kind of a visual sort of thing. All right. So we can come up with, just like we came up with the rate law expression, we can come up with a mathematical relationship of stuff when it's in that gray area, when it's at equilibrium. Okay? That's called an equilibrium constant expression. Another math thing. So in those 3 scenarios we looked at before, this actually is the gray area. It relates the molar concentrations of all reactants and all products at equilibrium. So that's the expression. All right, generic, 2 reactants, 2 products. So here's your first peek at a generic equilibrium constant expression. Looks like this. There's that other K I was telling you about. It's a capital K. This one has a subscript C. We'll be dealing with different subscripts. And actually, those little square brackets, they mean what you think they mean. Those little square brackets mean the molar concentrations of. And it takes this format, so kind of get your bearings about you. Notice what C and D are. They're products. Notice what A and B are. They're reactants. That's the format. That's how it works. That Kc is called the equilibrium constant. And of course, the bracket A and B are the molar concentrations of A and B. Now, here's the deal. Here's why this is just not a perfect world. We need to cover this and move on to Unit 3 material before you finish Unit 1. Excuse me, Unit 3 material before you take your Unit 2 exam. Those A, B, C, and D, notice where they are on the equation of interest. Those are stoichiometric coefficients. Notice where they appear in your equilibrium constant expression. They are the powers. Has nothing to do with reaction order, trust me. Okay, but those are the powers that you raise the molar concentration to. Take this mathematical equilibrium constant expression. So we do use stoichiometric coefficients for the exponent. They don't have any fancy names as far as I know. All right, so that big Kc, equilibrium constant. You'll be able to calculate Kc's if you know the equilibrium molar concentration of stuff. You just plug in. Or Kc's can be given to you. Equilibrium constant will be a constant for a specific temperature and specific reaction. That second note there actually kind of goes back to the 3 scenarios, kind of the 3 gray areas, where if you let enough time go on, basically you're going to hit a constant sweet amount of constant molar concentration of everything, reactants and products. It will stay like that. We talked about Le Chatelier's principle. We're going to talk about it again here. The Le Chatelier's principle, I can't remember the context we were looking at before. We're adding heat or subtracting heat. Basically, you can take something that's minding its own business in its gray area, okay, and you can shock it, okay, by adding heat or removing heat, or you can add a reactant or product. That's another way to shock it. And then kind of the bets are off. In some cases, you get a new Kc. In some cases, it just kind of settles into a new equilibrium concentration. All right. So we're a stickler for using units in this class. Of course, the brackets means moles per liter. And you're like, well, how does the factor label thing work out? If you're raising, the molarity to different powers, okay? Well, it's kind of a cool thing, and I'm not going to spend a lot of time, but basically we can think of those molar concentrations as being unitless. And don't sweat about it too much, but I did refer to the pages you need to see in your notebook, in your textbook, to kind of convince yourself. This is all to say that whenever you have your, and I'll put it up here, that equilibrium constant expression for A plus B will form C plus D. And we said it's the products raised to their stoichiometric coefficient, and the stoichiometric coefficient, small lowercase, okay, D raised to the D power, A raised to the A power, B raised to the B power. Okay, this is all to say that, we're expecting those concentration, or these units of moles per liter to cancel. But actually, these end up being unitless, so this is always unitless. That's my point. All right, equilibrium constant expressions. So I brought these down. This is on a previous slide. This is your kind of generic 2 reactants, 2 products. This is what the equilibrium constant expression would look like. So if Kc is kind of high, just generally speaking, and you're like, what does high mean? Well, you'll see some Kc's that are very high. And this actually will help you understand not only Unit 3, but when we talk about acids and bases, this will make more sense for acids and bases in Unit 4. Okay, if this is high, if this is large, okay, then that means that this is large. Okay, and what is that? That's the products. That's it. Okay, it means at equilibrium you have more products than you do reactants. Well, if Kc is small, and I'm going to show you some small equilibrium constants. Okay, if it's small, then it's the opposite. If that's small, then basically it's that you're dividing by a large number. Okay? Kc is small, that means that this is a big number, and that means that at equilibrium, your concentrations of your reactants is pretty large. Okay? And then, of course, something in between. If it's kind of in between, I see here it says 10 to the third, which is 1,000, or 10 to the negative third. Okay, if it's in between there, that means at equilibrium, you got a little bit of both. I think chemical equilibria are awesome. Because you figure we're used to basically starting with reactants, going to products, and that's the end of the story. Not so fast. So actually, this is an important slide, I think. They're all important, but... All right, so let's look at some large ones and some small ones. Check out that first one. Where basically, this is looking at the formation of water, okay, from liquid water, from gaseous hydrogen and oxygen. So 1.4 times 10 to the 83rd. Let's see, Avogadro's number is 6.022 times 10 to the 23rd. So you're like, dude, that's humongous. That means, like, at equilibrium, you basically don't have any of these left. You have a lot of that. So the next one, see calcium carbonate, chalk, right? Chalk is, none of us use chalk much anymore. Okay. Calcium carbonate can decompose into calcium oxide and carbon dioxide gas. But check out how small it is. Okay. So that is very small. So that means it does not go in the forward direction much at all. It's really hesitant. At equilibrium, basically, you only have a little bit of product, top, lots of reactant left. And then we have kind of an intermediate one. It's kind of a boring one. At equilibrium, between SO2, O2, and SO3, you basically kind of have similar concentrations of all those things at that given temperature. And then we have another small one. Carbon and water forming carbon dioxide and hydrogen gas. Pretty cool. Pretty darn cool. So let's talk about writing those expressions. There's just a few catches. In some cases, the catches I'm going to show you, the reactant or product doesn't show up in your expression. But we're okay for now. These are gases. So, again, I apologize a little bit because tomorrow you know that you cannot use the stoichiometric coefficient to use as a reaction order only if it's an elementary step. So, but these are equilibrium constant expressions. So let's knock this one out. So it's always products over reactants. So it looks like this. Product, O3 raised to its coefficient, divided by reactant, O2 raised to its coefficient. Next one, equilibrium. So we're going to have two things in the numerator and two things in the denominator, all raised to a stoichiometric coefficients. So the equilibrium constant expression for this equilibrium is this. NO2, molar concentration of NO2 raised to the first power, times the molar concentration of H2O raised to the sixth power, divided by the molar concentration of ammonia raised to the fourth power. Also in the denominator, the molar concentration of O2 raised to the seventh power. Now that's some crazy looking stuff. So I mentioned that sometimes that you're going to basically a reactant or a product will not appear in your equilibrium constant expression. And they fall into a couple of categories. One is water. Now, H2O a minute ago at that equilibrium, that last one, notice what phase it was in. It was in this gaseous phase. Okay, it'll always show up. But H2O with a little L next to it in its liquid phase will not show up if you have any AQs going on. I think we've got an example coming up. So, for instance, notice that we have H2O is not only the medium, but it's also a reactant. Okay, liquid water reacts with ammonia to give you hydroxide and ammonia. So we got the AQs going on. We have H2O in the liquid state. H2O in the liquid state will not appear in your equilibrium constant expression. So it looks like this. It's always products over reactant in this case. H2O does not appear. And notice that their stoichiometric coefficients are all 1, so they're all raised to the first power. By the way, this equilibrium constant is kind of on the low side. So what? It looks like it favors the reactant side. At equilibrium, the molar concentration of ammonia will be will be more than the products. All right. So the second one actually kind of has two. If next to the species you see either an L, meaning liquid, or an S, meaning solid, those things are also stricken from appearing in your equilibrium constant expression. And the thought there is that they are consumed, but they really kind of remain, in a sense, constant. I guess I should also say in their pure state. Liquid in its pure state. Okay, so here's an example of that. This is basically, let's see, AQ means water. This is basically dissolving silver chloride. We'll be talking about the whole dissolving process and its kind of description as an equilibrium. So if that's the case, I already told you solids don't appear. So it's always reactants over product. There's no product. Okay, so the equilibrium constant expression just looks like this, where it's the silver ion raised to the first power because its stoichiometric coefficient is 1. The chloride ion raised to the first power since its stoichiometric coefficient is also 1. Let's look at another example. Oh, I guess not. Okay. But you're going to have some examples. I am going to go ahead and assign this, and this will be due Friday. I'm going to show you what they look like, and I'm going to kind of apologetically explain that I took the easy way out, in that I left not much to the imagination to work these. Okay? So, because I could complain like this. You read this. This is assigned, right? The good thing, though, is they're all even. They're all odds, 1, 3, and 5, so the answer should be available under doc sharing. But basically, you have to turn those words into chemical equilibria. So I went ahead and did that. So what the heck, right? So the first one, when you kind of lift from the words to the paper, it looks like this. Basically, you have COF2 breaking down form CO2 and CF4. Everything's a gas. Notice I gave you a little warning up here. You have to balance it. The significance of balancing is to know, what power you're going to raise that to in your equilibrium constant expression. So balance it, write the equilibrium constant expression. That's it. I felt kind of guilty doing these because I thought, well, they might enjoy doing these. But then I thought, oh, well, that's okay. So B, when you read it a few times, it looks like this. Basically, solid copper reacting with the silver ion it's a redox reaction. Then silver is going to end up as a solid on the product side, and you're going to end up, instead of copper solid, you're going to end with copper ion. Okay? It's not balanced, but I think the coefficients of 1 are just great. My hint in green there is don't forget that solids do not appear in your KC expression. Looks like it's going to be a pretty boring KC expression, right? That's true. The last one, Peroxy disulfate, we use that. So peroxy disulfate, reacting with the iron +2 ion to form iron +3 and sulfate. So this one does need a little bit of balancing, right? Not too bad though. Looks like a 2 would do me, right? Over there. I don't see any solids or liquids, or water's not there, so it looks like those are all going to appear in your equilibrium constant expression. So the next one, that's not too bad. They give you the equilibria. I don't know why they did that before. In fact, I went ahead and did A for you. They're kind of fun. So it's always products in the top in the numerator and reactants in the denominator, all raised to the stoichiometric coefficients. And I think that should do you there. Oh yeah, I just said don't forget about solids and liquids. And I even put like little asterisks next to those. Oh, I missed one. Do you see the one I missed? Wait, this one? All right. Last one. So the last one, if you read it, says basically it wants you to it's kind of like, let's see, heats of formation a little bit, where standard molar enthalpy of formation, where basically, in this case, form 1 mole of HF. Of course, we'll need hydrogen and fluorine, but they are diatomic elements, okay? So don't forget to balance. Looks like a half a mole of each of those will form 1 whole mole of HF. And then write the Kc expression. Let's see if I had anything else to say. Oh yeah, I went ahead and the next one's 2 moles of ammonia from its elements in their standard states, which would be diatomic nitrogen and diatomic hydrogen. Again, balance it and write the Kc expression. And then the C looks like this. We're going to form 2 moles of N2O from nitrogen and oxygen, balance it, write the Kc expression. And then D, we're going to form 1 mole of ClF3 from Cl2 gas and F2 gas. Oh, and my little hint, remember? Since it's got an L, it won't appear. So this is kind of fun, guess what? So it's always products divided by reactants. So it's going to be 1 over log raised to its coefficient times log raised to its coefficient. So they feel kind of weird, but part of what I'm doing is to kind of get you, kind of pulling you through those. Okay, so those will be due Friday.